Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as surface tension. Let's see what do we understand by surface energy. What is surface energy? Surface energy of a liquid is equal to the potential energy per unit area of the liquid surface. Right? Surface energy of the liquid is equal to or is defined as the surface energy of a liquid is equal to the potential energy per unit area of the liquid. Right? So surface energy is nothing but it is the potential energy per unit area, or I could also say that it is the work done to produce unit area of surface. It is the work done or work required to be done to produce unit area of the surface, or I could also say that the work done required to be done to produce unit area of the surface is equal to surface energy. Right? So once we know what is surface energy, now let's see what are the dimensions of surface energy. Dimensions of surface energy. Now the definition says that surface energy is nothing but surface energy is equal to the potential energy per unit area. Since it is equal to potential energy, that means its SI units will be joules per unit area. So joules per meter square, right? And the CGS units will be dynes per ergs per centimeter square. Now once I know the units, I can find out the dimensions. I can say that dimensions of surface energy is going to be nothing but dimensions of work upon dimensions of area, right? Dimensions of work is nothing but force into displacement. Force is nothing but mass into acceleration, that is mass into displacement upon time square. So thus this will be m1 L2 t minus 2 upon area will be m0 L2 T0, right? Hence the dimensions of surface energy will be m1 L0 T minus 2. Fine, do we get this thing here? So surface energy is nothing but the potential energy per unit area. It is nothing but the potential energy per unit area. Fine, do we get this thing here? Next, let's see the next thing. What do we understand by surface tension? What do we understand by surface tension? Now, surface tension is defined as the tangential force per unit length in the plane of the liquid surface. What is surface tension? It is nothing but the tangential force. It is defined as the tangential force per unit length It is a tangential force per unit length in the plane of the liquid surface. In the plane of the liquid surface. right, acting at right angles on either side of the imaginary lines. Acting at right angles on either sides of imaginary line drawn, imaginary line drawn on the surface in equilibrium. Right? That means what is surface tension? Suppose if this is my surface of the liquid, say this is the imaginary line drawn on the surface of the liquid, then it is the tangential force which is acting at right angles to the surface, to the imaginary line drawn on the surface of the liquid. Fine, do we get this thing clear? Now, in that case, so this is what is the definition? It is the tangential force per unit length in the plane of the liquid acting at right angles on either side of the imaginary line drawn on the surface of the liquid. If this is the imaginary line drawn on the surface of the liquid, it is the tangential force acting on either side of the imaginary line. Fine, do we get this thing clear? Now, therefore I can say that surface tension is nothing but force per unit length. Right? So if this is the formula for surface tension, then I can say that the units of surface tension will be nothing but force, that is newtons per meter will be the SI unit and dynes per centimeter will be the CGS unit. Right? So those are going to be the units. Once you have this, then you can find out the dimensions also. Dimensions. So dimensions will be nothing but dimensions of force upon dimensions of length. Force is nothing but ma. So m1. A. Acceleration is displacement upon time square upon length. Length is going to be m0, L1, T0. So the dimensions of surface tension will be m1, L0, T minus 2. Fine, those are going to be your dimensions of surface tension. Right? Once you have this, next let's see. That means I can say that force is nothing but surface tension into length. Right? So the force acting on the line is nothing but the product of the surface tension into length. This force is always parallel to the surface of the liquid and acting at right angles to the length L of the imaginary line. So I can say that force acting on the line, acting on line L, line of length L, force acting on line of length L drawn in the surface, in the free surface, is product of surface tension and length right. This force is always parallel to the surface. This force is always parallel to the surface and at right angles to the length. Finally, get this in here. Now, the force, this particular force, or the force, it can be seen that the force due to surface tension is on both the sides of the line, and the resultant force on one side can be given by F is equal to TL, right? This force acts on both sides of the line. Right? So that is what is surface tension. Now let us try to find out a relationship between surface tension and surface energy. Relation between surface tension and surface energy. Right? Let's consider a rectangular frame ABCD. Let's consider a rectangular frame ABCD, of which you have wire PQ, which can slide without any friction on the frame ABCD, right? Now let us assume that frame ABCD is held in horizontal position and it's dipped in a soap solution, right? Hence there would be a soap film that would be formed on APQB, right? Now a force F will act on the wire PQ, right? So there will be a force that will be acting on the wire PQ, which will try to pull the wire inwards. Here you will have a soap film. There will be a soap film here, right? Once I immerse this, so there is going to be a force that will act on wire PQ that will try to pull the wire PQ towards AB, right? Now let us assume that L is the length of the wire of PQ. Let's just write this down. Consider a rectangular frame ABCD, right, of which another wire PQ can slide without any friction. Wire PQ can slide without any friction. Let frame ABCD be held in horizontal position and be dipped in a soap solution. Let us assume that it is dipped in a soap solution and taken out. Right? Hence, there will be a soap film APQB formed. Hence, a soap film APQB is formed. Right? Now, this soap film will exert a force F on wire PQ. Let F be the force on wire PQ due to surface tension of the soap solution. Tension of the soap solution. So this and it is going to, this particular force will try to pull wire PQ towards AB. Let F be the force on wire PQ due to the surface tension of the soap solution, which pulls PQ towards AB. Right? Now let us assume that L is the length of wire PQ. Let L be length of wire PQ. Length of wire PQ. If L is the length of wire PQ and T is the surface tension of the soap solution, T is surface tension of soap solution, right? In that case, I can say that the total force acting on wire PQ, total force acting on wire PQ. What will be the total force acting on wire PQ? Total force F acting on wire PQ is going to be, now force, we have defined that force is a product of tension and length. So the total force acting on wire PQ is going to be TL, right? It is going to be equal to 2TL. Question, why 2TL? The factor 2 is introduced because the soap film has two sides. There are going to be two sides of the soap film, the upper side as well as the lower side. So I'll just say that factor 2. Ideally, the tension should have been TL, but the factor 2 is introduced. The factor 2 is introduced in the above relation. Factor 2 is introduced in the above relation because the soap film has two sides. Because the soap film has two sides. Fine, do we get this thing here? And on both the sides of the wire PQ, and on both sides of wire PQ of length L, the force due to surface tension acts on it. Surface tension acts on it, right? So now I know what will be the force. Now once I know the force, let us assume that wire PQ is carefully pulled through a small distance x. Guys, can you see this? Let's assume that I pull wire PQ outwards by a small distance x. Let's assume that wire PQ is pulled through a small distance x to P bar Q bar, right? So I can say that if wire PQ is pulled outwards to a small distance x, then x to position P bar Q bar. Let's assume that it is pulled outwards to position P bar Q bar. That means if it is pulled outwards, that means I have to apply some external force. So let's assume that it is pulled outwards to P bar Q bar by applying external force. External force, say F. Now since there is force, there is displacement, that means some amount of work is going to be done, right? So I can say that work done by external force, the work done by external force against the pull of surface tension, the pull of surface tension, because the surface tension is going to try to pull the wire inwards, you are pulling the wire outwards. So in that case the work done will be nothing but force into displacement, applied force into displacement. Force we are saying is F, displacement is x, so the work is going to be force into displacement, but force we said is 2TL, so 2TL into x, work will be nothing but 2TL into x. But I could say that if A is the area, I can say that if A is the surface area, if A is surface area, then I can say that A is nothing but L into X. Length into breadth should give you the area of the rectangle APQB, right? In that case, I can therefore say that work done per unit surface area, work done per unit surface area will be nothing but work upon area. Work you just found out is nothing but 2TLX. Area is nothing but LX, right? Now, surface area. Now, if I'm considering surface area, I'll have to again introduce a factor 2 here. Why will I have to introduce a factor 2? Because I'm saying A is the surface area and the soap film is going to have two surfaces, one on the top and one below. So there are going to be two surfaces, hence I'm going to introduce a factor 2 in the denominator. So in that case, I'll get T. So therefore, I can say that the work done per unit surface area is equal to T. So the relation shows that the surface tension is equal to the mechanical work done per unit surface area. That's the relationship between surface tension and work done, right? So I can say that therefore surface tension, this relationship shows that surface tension is equal to the mechanical work done, equal to mechanical work done to produce unit area of surface liquid. That is what we have just derived. So this is the work done in producing unit area of surface liquid is equal to the surface tension, right? So this therefore can be another definition for surface tension. So I can say surface tension could also be defined as the mechanical work done to produce unit area of surface liquid, right? Now this work which is done is going to be stored in the form of potential energy. I can say that the work done is in producing the liquid surface, in producing liquid surface, the work done in producing liquid surface is converted into potential energy, right? Potential energy of the liquid surface hence I can say that potential energy per unit area of the liquid surface can also be called as surface energy. Potential energy per unit area of surface liquid. Potential energy per unit area of surface liquid can also be called as surface energy, is called surface energy. We have done this before. I'll show you. We have defined surface energy somewhere. Surface energy is nothing but it is equal to potential energy per unit area of the surface, right? So hence I can say that surface tension therefore is equal to the surface energy. Surface tension is equal to mechanical work done to produce unit area, and work done to produce unit area is stored in the form of potential energy. and potential energy is equal to the surface tension or is equal to the surface energy, right? Hence I can say that, therefore I can say that surface tension is equal to the surface energy of the liquid. Right? So this is the relationship between surface tension and surface energy. Surface tension is equal to the surface energy. Right? Now, but I can say that surface tension is work per unit area. Right? And now that I've said that surface energy is also equal to surface tension, therefore I can say that surface energy will also be equal to work per unit area, right? Now, in that case, the units of surface energy and surface tension should be the same. So, units of surface tension will be equal to joules upon meter square, that will be the SI units, or the CGS units will be equal to ergs per centimeter square. Those will be the units of surface tension, and the dimensions of surface tension will be nothing but the dimensions of work upon the dimensions of area. Work is nothing but force into displacement. Force is nothing but mass into acceleration into displacement upon area. So this is going to be m1. Acceleration is displacement upon time square. Displacement upon time square. This displacement multiplied by this displacement, therefore L2 upon area. Area can be written as m0 L2 T0. Therefore the dimensions of surface tension will be m1 L0 T minus 2. Fine, do we get this thing clear? Now, in that case, I can also say that the total work done in producing surface area A, total work done in producing surface area A, surface area A can be written as work is going to be surface tension into area, right? If T is equal to W upon A, then I can say W is equal to TA. So that will be the work done in producing a surface area A. Fine. Next, let's see the next thing. What do we understand by angle of contact? What do we understand by angle of contact? Right? Angle of contact. Now, angle of contact, when a liquid is in contact with the solid, the angle between the liquid and the solid, the angle between the surface of the solid, the angle between the surface of the solid and the tangent drawn to the surface of the liquid is at the point of contact is called as the angle of contact. See, for example, if I have a beaker, this is my surface of the liquid, right? The angle between the surface of the solid and the tangent drawn to the surface of the liquid at the point of contact. This is my point of contact. This is the tangent drawn at the point of contact. So this angle between the solid surface and the tangent drawn to the liquid surface at the point of contact is called as the angle of contact. the angle between the solid surface and the tangent drawn to the liquid surface at the point of contact is called as the angle of contact. So how do I define this? Definition: when a liquid is in contact, with a solid, the angle between the surface of the the angle between the surface of the solid and the tangent drawn to the surface of the liquid at the point of contact is called as the angle of contact, right? Measured on the side of the liquid. Measured on the side of the liquid is called the angle of contact. So, do we understand what is angle of contact? Now, the angle of contact, what are the factors on which the angle of contact depends? Factors affecting angle of contact, right? The first factor that affects the angle of contact is the nature of the solid and the liquid which are in contact. The nature of solid and liquid in contact, right? The second factor that affects the angle of contact is the cleanliness on the surface of contact. The cleanliness of the surface. The cleanliness of the surface in contact. And the third factor is the medium above the surface of the liquid. Above the surface of the liquid. So these are the three factors that affect the angle of contact. Fine, do we get this in clear? Next, let's try to find out the reasons for the shape of a liquid drop. Now, right in the beginning when I was explaining to you the molecular model, I had explained to you why you have a particular shape for a liquid drop, right? Now, let's consider a liquid drop. This is how the shape of the liquid drop will be. This is my liquid drop, right? Let's try to find out the forces that are going to be acting on it, right? So consider a drop on a flat solid surface. Consider a drop on a flat solid surface, right? Now, the forces that are going to be acting on it, right? There is surface tension force along the following interfaces. The surface tension forces acting on it are 1. Let's see all the different forces that are going to be acting on it. 1. There will be a tension between the liquid and the solid interface. The surface tension forces acting on it are at the liquid solid interface. right? Next, the air and the solid interface, air and solid interface, and the air and the liquid interface. Three forces are going to be acting on it. Right? Now let's see what will be the net result of these three forces. Let us assume that P1 is the force for the liquid solid interface. Let P1 be the force for liquid solid interface. So this force here is going to be T1, right? That's the force between the solid and the liquid. Let's consider that T2 is the force or the surface tension. T2 is the surface tension or the force for, say, air and solid interface. So this is going to be my T2. This is between the air and the solid. And third, T3. Let's assume that T3 is the surface tension between the air and the liquid interface. Surface tension between air and liquid interface. Right? So let's assume that T3, it is going to act tangentially at the point of contact. So these are the three forces that are going to be acting on the liquid drop. Now, in that case, for the drop to remain in equilibrium position, for the drop to remain in equilibrium, I can say that T2, the total force, the total surface tension acting between air and solid interface should be equal to T1 plus T3 cos theta. Yeah. Right? Now, for the drop to remain at equilibrium, T2 should be equal to T1 plus T3 cos theta. Therefore, I can say that cos theta is T2 minus T1 upon T3, right? In that case, now we will be able to get the shape of the drop. From this, we understand that the expression gives four cases. First, let's assume that T2 is greater than T1. If T2 is greater than T1, that means the surface tension between air and solid is greater than the surface tension between liquid and solid, right? In which case, if T2 is greater than T1, then cos theta will be positive. If T2 is greater than T1, then cos theta will be positive. If cos theta is positive, that means therefore theta will be an acute angle. If cos theta is positive, therefore I can say that theta will be acute angle. Right? Next, let's assume that if T2 is less than T1, if the tension between the air and the solid is less than the tension between the liquid and solid, in which case if T2 is less than T1, then in that case cos theta will be negative. Now we know that cos theta is negative only in the case of obtuse angle. Question: so how will you get an obtuse angle? I'll show you. Let's assume that this is your liquid drop. Right? Here this is your T2 this is T1, and here you will get an obtuse angle at the point of contact. That's how you will have an obtuse angle, right? This is T3, and this is going to be obtuse angle theta, right? If cos theta is negative, then I can say that theta, therefore I can say theta will be an obtuse angle, right? Next, if T2 minus T1 is equal to approximately equal to T3, let us assume that if T2 minus T1 is approximately equal to T3, in that case cos theta, guys, therefore what will cos theta be? Cos theta will be 1. If cos theta is 1, that means theta will nearly be equal to 0. Therefore theta will approximately be equal to 0 degree. That means instead of a drop being formed, you will have just a layer of water there. Fine, do you get this thing clear? Next, let's consider another alternative. If T2 minus T1 is greater than T3, right? In that case, if T2 minus T1 is greater than T3, then I have cos theta will be greater than 1. But can cos theta ever be greater than 1? From our trigo, we know that cos theta has to have a value between minus 1 and 1, right? So I can say which is impossible. Cos theta being greater than 1 is impossible. That means the liquid drop will never exist at equilibrium, right? In which case, if T2 minus T1 becomes greater than T3, then the liquid shall spread over the surface of the solid and the drop shall not be formed. Therefore, the liquid will spread over solid and drop shall not be formed. Right? Those are the 4 different types of drops that you can have. Fine, do we get this thing clear? So, do we understand this? Let's stop this here for the day. Thank you very much.